We're going to continue now with our discussion of change processes, but we're going to move on from constant volume processes to consider those that result from constant pressure. Now, let me remind you that from the first law, we have written this expression for the internal energy differential, that it's equal to a combination of incremental changes in heat and work, but that the work we can write as minus P dV. And under constant volume, of course, this goes to 0, so this would go to the heat change at constant volume. So how does all this change when we go to constant pressure? Well, in order to get a handle on that, I want to isolate the heat for a moment from this first equation and simply write out what the heat would be in terms of the internal energy and the change in work. And if we plug in P dV for the change in work, we'll find that du plus P dV would be our incremental change in heat. Now, in order to get more of a handle on this, I want to manipulate this P dV. I'm going to go over here to the side to write this out, but I'll note that if we ever were to take a differential of a product of two variables, that it would be equal to the differential of the first variable times the second plus the first variable times the differential of the second. All right, but if we have constant pressure now, this means that this d of the product PV is just equal to P dV. So in other words, this thing here would just be the product of PV at constant pressure. So what does that mean? Well, what we can do now is rewrite this expression for the heat, and now this is heat at constant pressure, so I'm going to put a little subscript on it, is equal to du plus P dV, which in turn is du plus the differential of the product PV. And now I can combine those and write this simply as the differential of the entire expression u plus PV. Now it's important to do this because all of the elements in this set of parentheses are state functions. So in other words, this thing that I've written out here is a state function, and I'm going to define that state function to be something new. I'm going to give it the symbol h, and it's called enthalpy. So in effect, our definition of enthalpy is going to be that it's equal to the internal energy plus the pressure times the volume. Now, and it's also related to the heat, and I left out the Q here. It's equal to the heat at constant pressure. So in other words, we have sort of an interesting relationship that when we have the incremental heat change at constant volume, that's equal to the differential of the internal energy. If we have the incremental heat change at constant pressure, that's going to be equal to the differential of enthalpy, this new state function. Now, are enthalpy and internal energy the same? Well, let's use a PV diagram to try to understand what their distinction is. So I'm going to draw on this PV diagram, I'm going to draw several isotherms. Remember that an isotherm was defined as PV equals constant. Let me write that out here. PV equals constant. So all of the isotherms are going to be these hyperbolic decaying curves that look something like this. And a way to read these is to realize that as we move outward from the origin, so as we move outward in this direction, temperature is increasing along that line. So if I were to have this lowest isotherm is at T1 and the outermost one is at T2, T2 would be greater than T1. It's always going to be true in these pressure volume diagrams that we've drawn here. I guess it's probably a good idea for me to label my axes here. It is a PV diagram. All right, now what if I were to imagine a process where I start at a point P1, V1 that's on this lowest isotherm, and I were to move to the outermost isotherm. So I've basically moved from T1 to T2. And I've done it so along this line that is vertical, so it corresponds to V1. It corresponds to a vertical constant V1 process. So constant volume process, which would take me from point 1 down here to point 2 up here, I could characterize as being, first of all, du along that path is just going to be the incremental change in the heat, but delta u along that path is just going to be the constant volume heat capacity times the change in temperature, where this change in temperature is just T2 minus T1. All right, so I can get delta U pretty easily from that, but this delta U is in turn just equal to the heat exchange that's done under constant volume process. Now what if instead I went from this innermost isotherm to the outermost one along a constant pressure curve? So I'm going to go from point 1 now to a new point, point 3, but point 3 and point 2 are on the same isotherm. So this would represent a constant pressure process. And in this constant pressure process, now the heat change along that constant pressure process is something that I get from this definition. It's equal to the enthalpy change for that process. I better make it a delta. Or I could write that the incremental change in heat along that curve is simply going to be the incremental change of the enthalpy, which is equal to the incremental or the differential change of internal energy times the differential of the product PV. Another way to write this out, by the way, is if I integrate it, I can write delta H is equal to delta U plus delta of PV. And that's a good way to distinguish these two things. All right, now I've made a point of doing this between two isotherms because I know that along an isotherm, if I were to go from 2 down to 3, the delta U change for that is going to be 0. So in other words, this is another way of saying that no matter how I go from that innermost isotherm out to the outermost one, the delta U is going to be the same. So delta U is the same here as it is here. These two are equal to one another. But the heat involved in that change is associated with a different state function. Does that make a difference? Well, in this case, I've got from 1 to 2, I've got delta U. That delta U now has to be the same as the delta U here in the process from 1 to 3. So if this delta U is equal to QV, then this delta U must also be equal to QV. But this delta H is equal to QP. So I can rewrite this whole thing. I've got delta H is equal to delta U plus delta PV. But for this particular set of changes, this delta U is QV, delta H is QP, and we can see that they are clearly different by this factor that involves the change in PV. Now the change in PV, we could also get using the ideal gas equation of state. Because we know that for an ideal gas, PV is equal to RT if we have 1 mole. So P1V1 will be RT1, P2V2 will be RT2, and the difference in these, delta PV, will be P2V2 minus P1V1, or R times T2 minus T1, or R delta T. So in other words, this thing here has the definition of R times delta T. And by this difference, QV and QP are going to be different. So enthalpy is going to prove to be a very important state function for us because it represents a state function that is relevant for constant pressure processes. And a lot of the processes that we do in a chemistry lab happen to be at constant pressure. And so that's why you may recall from general chemistry, that was the state function that we quoted most often when we talked about thermochemistry.